Can everybody see my screen?
Yes.
All right. Okay. Hi, everyone. My name is Neil, and I will be presenting as part of the ASDRP McMahon lab. Actually, one sec. Let me see if this works. Does presenting. Okay. Can you see the speaker notes tab?
Yes.
Okay. So let me see if I can share only the.
What you had up initially was perfect.
Oh, could you see the speaker notes slide?
Not initially.
Oh, okay. Let's see. I'm not sure if it lets me just share a single tab. So I can try to pull up the speaker notes on another device.
I believe if you bring it up and share it in slideshow mode, it will show you the speaker notes and it won't show them to us.
Okay, let's try that.
Let's try that.
Hopefully this will work.
Okay,
Okay.
it looks perfect now.
If I click on the presenter view, does it?
No. Go back to what you had.
Okay, because I can't see the speaker notes on this slide.
Okay. So you're gonna have to bring
Okay, let me grab another device and I'll bring up the slides or the speaker notes on there.
Fields are comfortable? The answer is no. There are so many designer fields that are easy to walk in, but this is not one of them. So save yourself $1,300 and have your boy.
somebody needs to mute Audrey.
The Wi-Fi fields are comfortable? The answer is no. There are so many designer fields that are easy to walk in, but this is not one of them. So save yourself.
Thank you.
You're welcome.
All right, hopefully this doesn't mess up the lighting, the screen and everything, but
Looks good now.
all right. So hi everyone, I'm Neil, and as part of the ASDRP McMahon lab, I will be presenting quantum computing error mitigation. Okay, so first, in quantum computing, we deal with quantum bits, also called qubits. Unlike classical computing, which is consisted of zeros and ones, quantum computing uses bits in superposition between the states of 0 and 1. Zeros and ones are represented by the two-dimensional standard unit vectors, and a qubit can be defined as a unit vector in the form of A times the 0 qubit plus B times the 1 qubit. Okay, so what is error? In quantum computing, there are two types of error. Bit flip error, where the 0 and 1 components are switched, represented by the matrix X on the left, and phase flip error, where the 1 component is multiplied by -1, shown by the matrix Z on the right. All other types of error can be seen as combinations of these two. Because these errors change the information stored in the bits, they can cause data corruption and incorrect results. Current error correction technology only lets through around 0.1% of errors, or 1 in 1,000, but physicists believe that an error rate of around 1 in a million is needed for any practical large-scale computing. So, mitigating error. How do we stop this error? So, in classical computing, the two most simple methods of error mitigation are the parity bit method and the repetition code method. First, parity bits. In the parity bit method, you decide whether you want to use an even parity bit or an odd parity bit. In this
You
example,
haven't,
we'll use even.
you haven't gone to the next slide.
Oh, next slide.
There you go.
All right. In this example, we'll choose even. Okay. So now we're going to use the string of bits 1101, as you see at the top of the screen, and determine its parity. Because it has an odd number of ones, we add the purple parity bit at the end to make the total amount of ones even, as we chose before. If an error happens, let's say on the second one, we will immediately know that something is wrong because the parity bit says that the string of bits has an odd number of ones originally before the parity bit was added, but now it has an even number. The pros of the parity bit method are that it detects these errors quickly and efficiently, as it only has to check if the parity bit matches with the bit string information. While the cons of the method are that it is weak against even numbers of errors, where the parity of the string of numbers would not change. Second, repetition code. Repetition code is a strategy where we represent each bit in a bit string as an odd number of its copies. In this example, we chose 3 copies. When an error happens on one of the bit repetitions, like in the second bullet point, we use the majority rule to determine what the value of the bit was before the error. The pros of this method are that it both detects and corrects the error, as we can see how the parity bit method doesn't actually correct the error. But the cons are that if there are 2 errors on the 3-bit string, let's say on the second and the third bit, majority rule would have corrected it to a 1, which is incorrect. Okay, next slide. In quantum computing, the basic model for error mitigation is the surface code. The diagram on the left shows a surface code as a grid of x and z squares. As you might recall, these are the same letters used to represent bit flip errors and phase flip errors, shown in matrix form on the right. On the diagram, however, these x's and z's are not in fact errors, but syndrome qubits, which are designed to detect their respective errors in the adjacent data qubits that are represented by the vertices. Data qubits are single qubits that actually hold the information in quantum computers. Syndrome qubits help detect bit flip and phase flip errors in the data qubits, and they do so in a very similar way to classical computing's parity bit method, by detecting any change in the parity of the data qubits they're connected to. The surface code also overcomes the parity bits method weakness of even numbers of errors by ensuring that each data bit only contains a single bit, and both types of errors are their own inverses. Each data qubit on the surface code is entangled with at least 1 X syndrome qubit and 1 Z syndrome qubit, protecting each data qubit from both types of errors. Now, error propagation. Error propagation in surface codes is when error spreads to other qubits from its source. In order to measure the propagation path, we use stabilizer operators. Each combination of 1 syndrome bit and its 4 connected data bits is called a stabilizer. So when measuring quantum error, we perform operations on each stabilizer formation in the surface code. Unfortunately, stabilizer operators can only detect the start and end points of the error propagation, and this adds the job of determining the path of the propagation, similar to how this connect the dots game on the right works. Unlike the game, though, we don't have a set space to fill up, and the error propagation could have taken any path to its destination. Now, the solution. Our goal is to introduce a method that computes surface code error propagations efficiently and effectively. Now, computing propagation, MWPM versus GNNs. The minimum weight perfect matching, or MWPM algorithm, is the most popular algorithm to decode the surface code. However, recently, models utilizing deep learning have demonstrated higher accuracy in decoding surface codes. There have been 3 papers published which have explored the applications of graph neural networks, or GNNs, to error correction on surface code. All of these papers found that graph neural networks are a feasible error correction device for this problem. This is because graph neural networks are specially designed to work on structures of points and connections. The diagram on screen shows the layers of a simple GNN model and highlights the operations the model performs on each vertice of the graph. Okay, now we can apply our GNN model to the surface code by redefining it in a grid-like shape. If we think of the data qubits and the syndrome qubits as points and their entanglement as the connections, we can successfully apply the graph neural network to the surface code in order to detect the error propagation path. As you see on the screen, this is an example of how we would organize them. Now, the data. In order to collect data to train our model, we need to find a way to purposefully inflict error on the surface code. This introduces us to bosonic baths. Bosonic baths are environments of tiny particles called bosons. These could be particles like photons, light particles, or phonons, sound particles. When a surface code is immersed in a bosonic bath, the bosons interact with the qubits and can cause errors and error propagation. Think of the bosonic bath as an extreme simulation of the qubits during computations. The bosonic bath allows us to quickly and efficiently gather data for our model that is realistic for application. We also use a correlated noise model as part of our data. A correlated noise model is a model that predicts how correlated noise that propagates errors through multiple qubits, will affect a quantum system such as the surface code. We will use this model to provide data for our graph neural network in order to increase the accuracy of our model. Okay, so as a summary, here's a timeline of how our project will work. First, we'll start with collecting data. We'll generate the data of the surface codes and incorporate a bosonic bath model into the surface code data. We'll then simulate the surface code with a noise model and create a dataset of the surface code with the new error patterns. Then we'll set up the GNN model by representing qubits as nodes and the entanglement between them as edges. We will develop the GNN and train it on the simulated surface code and noise model. We will then evaluate the GNN model's performance, and finally, we'll implement an MWPM model and assess the performance relative to our GNN model. We expect that our GNN model will perform in a higher accuracy than the MWPM model. Okay, thanks so much. We'd like to acknowledge and give many thanks to Dr. McMahon and ASDRP, and credit for inspiration that was taken from previous work done on a similar topic by Pranav Gupta, Rohan Vig, and Dia Vatsavai. Any questions?